Hi everybody, this is Konstantin Läufer, your Comp 413 instructor here at Loyola University Chicago. And today's video is about software design patterns, part 1. And let's start with a definition from the rather accurate Wikipedia page. And according to this, a software design pattern is a general language-independent reusable solution to a commonly occurring problem within a given context in software design. And by contrast, a programming idiom is a language-specific solution to a commonly occurring problem, and a software framework is usually language and domain specific. So, for example, the Swing GUI framework for Java. And let's start with a brief history of design patterns. And as I'm sure you've noticed by now, in computer science, especially software development, we like to take inspiration from actual building architecture. And that's where, for example, terms such as software architecture, enterprise architecture, etc. come from. And for design patterns, there's also an important inspiration from architecture in the form of this book by Christopher Alexander and his co-authors called A Pattern Language, which was about timeless solutions, recurring solutions to problems in building architecture. And Alexander and his team basically documented what they've observed in actual architecture and expressed it in the form of this pattern language, which is kind of a collection of interconnected patterns. And in the early 90s, a lot of the people working on frameworks, software frameworks, were recognizing a similar phenomenon in software, and that got later generalized to other areas, such as enterprises, organizations, and so on. And the seminal book was this Design Patterns, Elements of Reusable Object-Oriented Software by Erich Gamma, Richard Helm, and Ralph Johnson, whom some of you saw a few weeks ago during his presentation, and John Lycides. And this is the first, let's say, attempt to do something similar as Alexander had done for these building architecture patterns, but for software design patterns. And this book is referred to as the Gang of Four book. And you will see people talk about the Gang of Four patterns, Gang of Four catalog, etc. So that's what this is referring to. And almost around the same time, some other groups were also working on these ideas. So Bushman and some other volumes in this series that also involve Doug Schmidt, they were looking more at telecommunication and distributed systems patterns, whereas the Gang of Four were looking mostly at GUI patterns because they were coming mostly from the world of GUI frameworks. So I would say both of these books mark the beginning of this practice of documenting and sharing good design in the form of design patterns. And the emphasis is really here on describing what professional developers consider and use as a good design practice. So this is a descriptive effort as opposed to a prescriptive effort. On the other hand, you could say, well, once you have this documentation of what works, then it becomes prescriptive when you're trying to learn how to do things right. But the initial intent is really to say, well, what's out there, and that's really what makes it a pattern, the fact that many people use that same approach over and over. That's what makes it a pattern. And in that sense, it's a descriptive approach to document what's out there and what's been working. So let me give you a quick overview here. So Vince Huston has put together this thing that looks like a periodic table of the elements, organizing the Gang of 4 design patterns. And there are 3 categories here. So the yellow ones are on the left are the creational patterns. The ones in the middle are behavioral patterns, and the ones on the right are structural patterns. And as Ralph Johnson said in his talk, the creational ones are diminishing in importance now that there are techniques such as dependency injection containers, etc., such as Spring, that take over some of those responsibilities. So we're going to focus mostly on structural and behavioral patterns. And we'll come back to this resource shortly. And I just wanted to show briefly that there's there are a few different common forms of describing a design pattern. And we'll start by looking at an old friend, the iterator pattern. And we'll see the description in these kinds of standard formats. And if you look here, there's a mapping here in the middle between the canonical form, which has these sections, to the Gang of 4 form, and then an increasingly common form is this kind of hybrid that's down here. And let's see. Let me actually pull up the iterator pattern here. Okay. And here's a description of that. And let's actually go to the iterator pattern. And that says here as the essence, or meaning the intent, to provide a way to access the elements of an aggregate object sequentially without exposing its underlying representation. And let's look at this problem a little bit. So here on the left, there are these different attempts to solve the following problem, which is adding the items in a list, assuming the items are numbers. And let's start by saying, well, we don't really need an iterator for this. We could just do this using the list interface, and we can say, well, my list could be any kind of list, like an array list or a linked list, and we can just do it like this using the get method that accesses the ith item in a list. Okay, so in fact, this solves the problem of adding the numbers, and it does this without actually exposing the underlying representation. So this works whether it's an array list or a linked list. The get works either way because we're writing the solution against the list interface without making any assumptions on the underlying representation. But there is something really bad about this solution here. Okay, this one. What is it? Well, ask yourselves about the performance. And when you have a linear collection and you want to traverse it linearly, anything other than spending basically a constant amount of time with each item and moving from one item to the next is unacceptable. But the get, when you're doing this for a linked list, the get has to start at the beginning. So with each get, you lose your current position and you start from the head of the list to navigate into the list to the ith node that contains the ith item. So this is simply unacceptable because it's disqualified because of the really bad performance. Well, okay, let's go back to the drawing board and say, okay, well, we got to do it maybe in specialized ways. So for linked list, we'll say, okay, let's start with a head node and then iterate through the nodes one by one. Okay, so this does the same thing. It adds up the items and it does it efficiently, but we lost the abstraction. And then just for completeness, even though the get works efficiently for an array list, this is what it would look like, what the summing up the items would look like for an array list with the abstraction exposed. So what we see is a trade-off here. So either we have the abstraction at the expense of performance, that's what we have up here, okay, or we give up the nice abstraction that makes our solution implementation independent, and we get the performance back. So this is a typical trade-off, and many design patterns are intended to solve or reconcile these kinds of trade-offs. Okay, well, what we need to do is think out of the box a little bit. So the problem is that we use the list abstraction as the interface based on which we designed our solution. The problem is the list interface has this get method, but it doesn't have a method that captures this idea that we are this far into a linear traversal of the linear collection in an abstract sense. So that's the kind of abstraction that we need to bring in, and that's exactly what the iterator is. So if we wrote the solution, assuming we already have this iterator abstraction, which in Java has a hasNext method and a next method. The hasNext tells us whether or not there are more items coming, and the next returns the current item and switches to the next item in one step. So this is what it would look like, and what you see, as the for syntax, the enhanced for syntax in Java, which would be for I colon my list. That's an abbreviation basically of the iterator approach. So it translates kind of to this approach where we're using an explicit iterator. So what we have here is a solution that achieves the objective of adding up the numbers, but you're seeing here that this works for any list, regardless of the implementation. So we got the abstraction back, and if we look at this little journey that we went through, what it took was to question what the right abstraction was, and to recognize that in this case the list interface did not support the idea of expressing a current position in a traversal, in a linear traversal, and that meant, well, we had to restart every time. In the case of a linked list, we had to navigate from the beginning to the desired node and then get the item stored in that node, and that killed performance. And by thinking out of the box and recognizing this new abstraction, we were able to get the performance back and keep the idea that our solution should be abstract and implementation independent. So the question is then, how can this work? There must be some kind of magic, but really there isn't any magic. It's just, and that's why I gave implementation specific solutions for both the linked list and the array list, because there you can kind of see, when you look at the highlighted code here, you map it back. You can reverse engineer then what the iterator implementations should be like, and those are given here. So if you see, for the so each iterator needs a way to represent the current position, and for the linked list, that's the pointer to the current node that starts with the head of the list, and then with next you move on to you move on to the next node, and then you return the item at the current node. So that stuff's here, right? And has next is simply checking whether we've reached the end of the list. And then for array list, the position is just the index into the array, and has next just means, well, as long as we're within the bounds of the array, we have more items coming. And next will return the current item and increment the iterator position by 1. So in the end, it's all pretty straightforward. Anyway, so this was my attempt to reconnect you, to introduce you to patterns by reconnecting you with a familiar abstraction, which is the iterator, and kind of revisiting where it comes from this kind of pattern standpoint, meaning looking at the trade-off that we face and bringing in an abstraction or a design pattern to address and reconcile this trade-off. Very good. And then we have a few Android examples where we can observe certain patterns as well. And but before we do that, let's just look quickly at the iterator description here in Huston. So it basically matches what we were seeing here, so he elaborates more. This is similar to what you would see in, let's say, the Gang of Four book with all the sections fleshed out, and examples, different kinds of trade-offs, ramifications, rules of thumb, etc. Okay, back to the overview here. And let's now look at the simple batch Android Scala example and the patterns that are represented in that. So in this example, the main activity in the onStart method creates a so-called concrete batch task, and it passes to that an object that has the word strategy in the name, and this one says text view output strategy. And then it says, okay, let's run the batch task. So let's try to make sense of all of this. Okay. And basically, the purpose of this example is to introduce you to these two simple patterns, command and strategy. And command is an object that represents something like a task or so. So where you can represent the task as an object, and then you can perform that task at some later point after you've created the object. And in some versions of the command pattern, you can equip those command objects in such a way that they also know how to undo themselves. So in that way you could get undo and redo functionality, and in the second chapter of the Gang of Four design patterns book, there's a nice example where they show that. This is a fairly complete example. So here, this doesn't have undo. This is a simpler command pattern example. And if we go back here and we can look under model, and there's a little bit of a framework which gives a kind of support structure for us to use the command and strategy patterns in this particular application. And there's an abstraction called abstract batch task, and that extends runnable. And often when you see runnable, that suggests that there's some kind of command pattern at work. And this depends on an output strategy. So meaning it has a reference to, so it depends on the output strategy. And what it will do is provide, based on the output strategy, these print methods, these additional print methods. So being able to do a print ln, whereas the output strategy just defines a print method. And for us to define our concrete task, such as print the squares of the first 100 numbers, for example, we could implement an abstract batch task, and that gives us access to these print methods that use the output strategy that we would provide as a pluggable parameter. So that's basically how strategy works. So it's a way to plug in such a way that you have different choices, typically. Plug in a piece of your functionality. Okay. A good example of the strategy pattern is also in sorting. Let's say you write a sort algorithm, and you might want to sort in ascending order in some cases and in descending order in other cases. And really the only thing that changes, if you look at the ascending sort and descending sort side by side, is the comparison you use to decide which items should come before the other items. And that is a really good example of the strategy pattern. If you say, well, let's factor out the comparison as a strategy, kind of as a parameter, to the sorting algorithm, so that I can provide that when I invoke the sorting method as an argument to that method. And that argument would be an object that encapsulates the comparison method. Okay, so in an object-oriented language, that's how it would be. And in languages that have syntax for functions outside of an object, for standalone functions, this would simply be called a higher order function, where the function takes that other function, in this case the comparison function, as an argument. So a higher order function is a function that takes one or more other functions as an argument, and that would be the more concise functional language equivalent to many situations where on the object-oriented side you would use a strategy pattern. Okay, so let's see. Coming back to, let's bring that over here so we can look at it side by side. So here is a specific output strategy which implements the print method by appending a text to an Android text view on the Android screen. Okay, so what we are achieving here is we're now going to be able to express a concrete batch task in such a way that it will work for any output strategy, and we can plug in, if we want to use this batch task on Android, we plug in an instance of the text view output strategy. And if we want to use the same batch task in a console application, we could plug in a console output strategy. And we wouldn't have to change the batch task at all. So that's the beauty of expressing the algorithm with respect to an abstraction, and that abstraction becomes a strategy that we can plug in. So the main activity is here, and we still have to find the concrete batch task somewhere. So anyway, in the main activity, we're creating the concrete batch task instance, and we're parameterizing it for running this batch task in such a way that we can see the output on our Android screen. We're parameterizing it by a text view output strategy. So let's look at the concrete batch task, and that should be here indeed. And that says, okay, well, we'll print a table of squares. And you see how this knows nothing about Android, and the fact that it's supposed to show up on the Android screen is achieved by plugging in the a suitable output strategy. So if we look at the description of the strategy pattern, we'll see that this matches the kind of context and intent. You're also seeing here the command pattern in the form of the concrete batch task. You know, we're able to create an instance of this class that encapsulates a task, which is this sequence of steps. Okay, and it's not going to run until we actually invoke the run method. So we could pass this around as an object until someone decides, okay, let's run it now. And you know, that's let's see. That is not quite obvious here because we're creating it and then running it immediately. But you still see that we have to invoke the run method explicitly, and that invokes the highlighted code over here on this side. Okay, so the command pattern is here. So an object is used to represent and encapsulate all the information needed to call the method at a later time. So that's the task of printing those numbers in this case. And this is a relatively simple example of a command pattern. Again, you would have more state inside the command pattern if the command needs to be able to undo its effect. In this case, we don't really have any state other than the reference to the strategy. And then the strategy pattern is here, also known as the policy pattern. So it enables an algorithm's behavior to be selected at runtime by plugging in the desired strategy. So in the case of the comparison method and the sorting algorithm, so the sorting method would be the family of algorithms, and then rather the comparison would be the family of algorithms that's encapsulated, and you plug in the desired strategy representing the comparison method for ascending or descending order. Okay, so in terms of the structure here, the context would be the sorting algorithm. Okay, so let's move on to the next set of patterns here. in the context of the shapes example, which you're intimately familiar with now. So in the shapes, what we're doing is, let's pull that up. In fact, oops, let's pull up rather the, let's see, the project. And in the shapes project, we have a predefined hierarchy of case classes, and in fact, let's actually look at the Java version first, and then tie the connection to the Scala version. So here, let's see, so we have the model, which has this shape interface, and the only behavior it has is this accept method. Okay, and that's for the visitor pattern. You can see here there's a visitor as an argument, and corresponding to that argument type, there's a visitor interface, and it's generic in terms of the result type, because as you saw, for example, the size behavior should produce a number, whereas the bounding box behavior should produce a bounding box. So these are of different types, and that's why you want the result types of the visitors that represent these behaviors to be generic. And what you see here is a visit method, which here I started to call on this, on that, because when the visitor sees a particular node in an object graph, it's a little bit like an event. And you will see that down the road when we look at event-based execution and event-oriented style of applications, which of course plays a role in anything user interface, anything that has a user interaction. Okay, so then, so these visit methods, okay, they're there because they're the corresponding shape implementation. So for example, circle implements that shape interface, and in the accept method it says, it tells the visitor that the visitor is looking at a circle. So the accept method is for initiating the process for the visitor to visit a data structure or object graph. Okay. And what else do we have? So let's look at, for example, rectangle. So that looks basically the same. So it also says visit me and I'm a rectangle. Okay, that's what the accept method does. So for each kind of shape, the accept method tells the visitor what kind of shape it is by invoking the corresponding on that type of shape method. Other than that, these shapes have just whatever attributes they have to have. So a circle has a radius and a rectangle has width and height, and what they don't have, notably, is any location information. How can that work? How can you have rectangles that are all have their top left corner at the origin? Doesn't seem to make sense. But the idea is, well, instead of implementing these additional attributes within each kind of shape, we could say, well, that would be a lot of repetition if we had to have location information in a circle, location information in a rectangle, and in all the other shapes. So we say, why don't we have an object that represents location information, and then we can wrap that around a shape. So if we want a rectangle at a different location, we can wrap a location object around it. Okay, so location says, okay, I'm going to wrap around a shape, meaning it has a child or a sub-object that it refers to that's a shape. So it could be any other kind of shape instance. And it adds the location information here. And that's a typical example of the decorator. What we see here is location is a shape, meaning it maintains the interface of shape. So it has the same behaviors as other shapes, which in this case is just the accept method. And it also has a shape, which is the child around which it wraps and to which it adds the location information. So this is how the decorator pattern works in a nutshell. Preserving the interface, meaning there's an is-a relationship, and then there's also the has-a relationship, meaning the decorator wraps around an original instance. Preserving the interface and adding additional kind of enhancing or modifying the behavior accordingly. Okay, now what about the situation where we want to treat several shapes as if they were a single shape? So we want to put them together, and then we might want to drag them as one unit, or let's say shrink or enlarge them as a single unit by interacting with them as a group or composite of shapes. So in graphical drawing programs, this is usually called grouping, right? So you can have several, let's say, circles, rectangles, and so on, and then you can say, let's form a group, and then you can move that group as a single unit, and all the shapes kind of move along with, as a group. And that, let's see how we can achieve that. We can say, well, we have a list of shapes that are the pieces of the group or parts. So, and the other thing that we have, well, we want to be able to treat the group as a shape. So that again gives rise to the two relationships. So group is a shape, as well as group has 0 or more shapes. So in the UML diagram you would see that there's an is-a, so group is a shape, and group has 0 or more shapes. And this allows you, so the has-a relationship allows a group to group multiple shapes together as a single object. But by saying, well, that single object also has the shape interface, you can use the group as if it were just like any other shape. And that also allows arbitrarily deep nesting of these groups. So you can form arbitrarily deep hierarchies. So for example, in an organization chart, you could have persons, and then you could have a grouping node, which would be the organizational unit. You could say organizational unit implements node, and it also has 0 or more nodes, and then you could use that to build arbitrarily deep organizational hierarchies. All right, so now the visitor works like this. So one key aspect of using visitor is to decide ahead of time and build that decision into the common interface. So by saying, well, shape has, instead of having specific behaviors such as shape having the ability to tell you its size or tell you its bounding box or drawing itself onto an Android screen or a Swing screen, Okay. Instead, we're just saying, well, we're not building any behaviors into shape and its implementation classes. We're just equipping it with the ability to accept a visitor and the corresponding implementations here, such as the implementations of the accept method telling the visitor what concrete implementation it is looking at. So thereby accept method in circle telling the visitor you're looking at a circle, and then pass the object itself so that the visitor can then perform the behavior. Okay. And that allows us to express behaviors outside of the objects to which these behaviors apply. So here's, let's say, the size visitor, and that has implementations of size. So these are, of course, dummy return values, because this is your job to implement them with the right return values. So the behavior, the key insight here is that the behavior is expressed entirely outside of the data structure. So the data structures, meaning in this case the shapes, have no behavior other than this ability to accept a visitor. So they are just structures, okay? And the visitor provides these behaviors separately. And what you're seeing here, just as a brief digression here. So visitor is a behavioral pattern, that's the V down here, and composite and decorator are structural patterns. So also, by the way, command and strategy are behavioral patterns. Okay. But so this is striking, the fact that composite and decorator are structural patterns, because their purpose is to allow you to build structures, and then visitor will add the behavior. Now, we could have chosen a non-visitor based approach. Okay. So what if we had said, well, every shape should know its size, every shape should be able to tell you its bounding box, and every shape should be able to draw itself to an Android canvas. Well, let's look at that visitor first of all here. So here it is. Okay. And see here how, for example, this draws a circle, and you've seen this kind of code as the Scala version of it. Now, what are the consequences of using the visitor approach versus not using the visitor approach? One thing that you should see immediately is that if the shapes know how to draw themselves on an Android canvas, there is immediately a coupling or dependency of the model, this graphical shape conceptual model, and the Android framework. So is this good or bad? Well, you could argue it's actually really bad, because it means now these shape models will not work outside of Android. You have to have the Android framework present to be able to use your shapes, even if you're not interested in drawing them on an Android canvas. So the visitor pattern decouples very nicely these kinds of specific behaviors that might have very specific environmental dependencies from the actual structures. So this is a big advantage. And then there's another advantage of visitor, which is if you have a relatively stable data model, but you like to introduce behaviors left and right frequently, then you can introduce these behaviors like size without touching the data model. Okay, So it's easy to add behaviors because you don't need to go into each class in the data model or domain model and touch that. By contrast, if we didn't have visitor and we wanted to add a new behavior, let's say draw, we would have to add it to the shape interface. We would have to add a method, and then we would have to track down each implementation of that interface and provide a corresponding method implementation. So that would be a much harder change that kind of pervades a much larger portion of your code base. Okay. On the other hand, if your data model changes frequently, let's say if you want to introduce another shape such as ellipse, what does that mean? I'll leave that as an exercise. So what is the consequence for the visitor interface and its implementation classes if you added, let's say, an ellipse class? What would have to happen to the visitor interface, and what would have to happen to its implementations like bounding box, etc.? Okay, so that's something I'd like everybody to think about, and we can have a discussion about in our group. Very good. So now finally, the Scala version of the shapes example, which you're very familiar with now as your project 2, the decorator and composite patterns are the same. So if we pull up the Scala version, let's verify that. So here, so the shapes are here, and you see how location has a shape as a child. It adds the location information, and it extends, meaning in Scala there's just extends, there's no implements. So it means location is a shape. So location has a shape, that's the child, and location is a shape. So it's fully equivalent to decorator patterns in other object-oriented languages. And then the same thing for groups. So val children, var arg shape, so 0 or more shapes, and it has a 0 or more shape, and it also is a shape by extending the shape trait. So same thing. But the visitor is actually not apparent here because shape doesn't even have a method, the shape trait. And what happens here is, so in the object-oriented approach, behaviors are chosen dynamically based on the class of the receiver object. And in the visitor pattern, we're basically working around that in such a way that we can pull out all the behaviors without having to have a branching construct, like an if-else. For example, if I'm looking at a circle, then let's do this. If I'm looking at a rectangle, then let's do this other thing. And that's achieved with the way the accept methods are written. So the accept method is chosen based on the receiver object in my domain model instance, and then that tells the visitor what kind of node it's looking at, and that identifies the behavior that applies to that node. Whereas in Scala, because Scala has pattern matching, this same effect can be achieved more directly. So if we look at the size method, we can, well, the size method doesn't really have a specific pattern, but looking at the bounding box, we can say, okay, well, if we're looking at a circle, we're doing one thing. If we're looking at a rectangle, we're doing another thing. So because it has this pattern matching, the branching is kind of a cleaner construct than, let's say, if-else based on the class of the argument. But ultimately, it boils down to the same kind of behavior. Okay, so, but it's not considered good object-oriented style to have a lot of branching on the class of an object, of the receiver object, but it's considered perfectly reasonable Scala style to have a behavior that pattern matches on the argument. So in sum, that's why in Scala you can express these kinds of behaviors outside of the domain model classes or data model classes, using pattern matching, and you get basically an ordinary recursive function. So you don't really need a visitor pattern. Then finally, there's also this question: what happens? I mean, can you somehow keep the visitor style but handle extensions to the domain model? And there's some work on that, but it's a bit. I would say it's a little complex, and it's more of an advanced topic. So, in general, the rule of thumb is if your domain model evolves and your behaviors are usually the same or stable, then you're better off without a visitor. And if your domain model is stable and your behaviors evolve, you want to add different behaviors frequently, then the visitor pattern will help you. And of course, the other comment that I made earlier, that using the visitor pattern or the Scala equivalent here decouples your domain model from other dependencies. So in that sense, those visitors kind of mediate between the a very reusable domain model and very specific dependencies that certain behaviors have. Okay, so this has been quite a bit of material, and I'm looking forward to discussing any comments or questions you might have in our group. All right, have a great weekend.